definitions of functions. So from the graph y equals fx. Now notice here, this is fx. Okay, so this is the graph. This is the function fx. So this information that we're going through now relates to any function. Okay, so I've tried to draw different diagrams when we're going through them to highlight the fact that it doesn't matter what the original function looks like. These transformations affect them all in the same way. So the first one, so if we have some kind of original function with a number added onto it, we know that the graph of the original function fx is going to move by a units in the y direction. Another way that we often say is it's translated by 0a. And we know that we use this as our translation vector because the top number tells us our horizontal movement and the bottom number tells us our vertical movement. Okay, so if this was our original function, the straight line, if the value was positive, then our this distance here is a, so this would be fx plus a. Let's just use. Obviously, if a was negative, then the function would have moved down. Do you want to put one of those on there as well? Let's do that. So this would be fx minus a.
So is this like...
Okay, so next one. Do we know what kind of graph this is? Have we seen this before?
Wait, is this cosine?
Sine or cosine, yeah, lovely. Okay, you should have met these originally at GCSE. We're going to look at them in more detail later on. But the transformation of them makes no difference whether, as I say, these transformations happen to any function. So if we have f of x minus a, now note this time the a is inside the bracket. Okay, so an example, like a common example we would look at is something like x minus 4 squared compared to the x squared graph. Okay, so the difference is the 4 has gone inside the bracket. If you recall when we were specifically looking at parabolas, we know that whatever value is in here, it's actually translated by a units in the x direction. And that's when it's minus a. Okay, so if it was minus a here, it would translate using by a units. So again, we could say translated by a 0. Okay, that's using translation vectors as opposed to just words. Either are acceptable. So a would be on top of that one because it's a horizontal move.
Wait, how do you know it's horizontal?
Because it's inside the bracket. So the first one was outside of the bracket, it was stuck on the end, so that's why we knew it was a vertical movement. This second one is inside the bracket, and so it's a horizontal movement. But it is important that you recognize that it's x minus a, and that's why it's translated by a. If you, for example, had f of x plus 2, we would have a translation of negative 2, 0. Yeah?
Is that just for beautiful graphs?
No, it's for any kind of graph, and that's what's important. That's why I've got these different pictures here, because if a function has been changed in a similar way, so for example, if we had a y equals x plus 4 cubed, we know it's a cubic graph, but we know it's not the normal basic cubic. It's actually shifted left 4 units. Any kind of function, if it's inside a bracket, it's a horizontal shift. Okay, so if this was my original function, it doesn't really matter if we go left or right. Let's go left. Oh. Oh, that wasn't great. So this whole graph has shifted by a unit to the left. So this blue function would be f of x plus a because it's gone to the left. Okay, if I were to move to the right, it would be x minus a. And I've tried to summarize that over here. So if it was x minus a, the graph shifted right. If it's x plus a, the graph shifted left. Alright, so if we have a negative sign in front of the graph, this reflects it in the x-axis. Okay, so here we have our original, and happens to be a parabola. If it was negative fx, it would just be a reflection in the x-axis. Oh, that's not too shabby. Okay, so if the negative sign is in front, it's just a reflection in the x-axis. Alright, so the next one. So this is where the negative sign is inside the bracket, okay? Because the negative sign is inside the bracket, this one is a reflection in the y-axis. So if that was my original function, this would be f of minus x, because I've reflected the whole function in the y-axis. Okay, so the next one. This is where a number is stuck in the front of it. Okay, so if there is a number stuck in the front of the function, then we know that the graph has been stretched parallel to the y-axis. So it's an up and down stretch by a scale factor of a. Okay, so what that means is that your x values don't change at all, but your y values are pulled up or down, as the case may be. So, for example, I may have a graph that looks like this. Okay, so you can see that it crosses the x-axis in the same place, but your y values are a times bigger. So this one looks like a would be 2, because it's twice the height. Okay. So that's if the a is in the front. As always, what if the number was inside? So if the number is inside, then the graph is stretched parallel to the x-axis. So this time it's been squished or lengthened in the horizontal direction. Okay, so the first, when the number's in front, it's stretched in the y, but when the number's inside, it's actually the horizontal direction. But notice the scale factor is actually 1 over a. Okay, so for example, if we had a function of f of 2x, then the original graph would be half of the width of the first one. Okay? Whoops. So if I had this one here, I would be crossing here, maybe here. Oh, that's not awesome. But so this would be, for example, if it was f of 2x. I've gone half of the distance. Half of the, width across. Okay, so that would be when it was a 2x. If we had f of a half x, or x over 2, which is obviously the same, then it's actually going to take double the amount of time to do this. So where my original coordinate was whatever this one is, we're going to it's going to be over here, and this one would be over here maybe. Not beautiful, but hopefully you get the idea of it. The reason being is obviously because 1 divided by 1/2 ends up being 2. So it's taking twice the amount of time that it usually did to form the graph or form the function.